Hello, my friends, and welcome to this course on Hex-Mesh generation and processing. This is a joint collaboration with Marcel, Alain, Gianmarco, David, Xifeng, Ricardo, Frank, Jean-Francois, Marco, and myself. And you can have and see more material on the survey we published in IECM transactional graphics or the material of this course. So we'll try to fit as much more information in the next couple of hours. So about the speakers of this course, there are two main speakers, myself, Nico Pietroni from University of Technology, Sydney, and Marco Livesu, who is a researcher also at University at CNR of Italy, an institute called IMATI. So he both works in Hex-meshing. And first of all, I would like to go with an introduction and tell you a bit more about what this course is about and why hexaedral meshes are important and why they are useful. So what is an hexaedral meshes? Well, basically, you all know the concept of meshes, where you have a set of elements that are interconnected and they create a shape. Usually, we see this kind of meshes for surface, but actually there is also meshes that model the volume, right? So in this case, you can see here in the image on the right, that's been created using Hexalab, which is a software that we released a few years ago, that these kind of X meshes, they are composed by cubes that are interconnected together inside the volume. So, and how these cubes are interconnected? Well, let's see a bit of the structure of these X meshes, right? To start a bit from the basics, so we know a bit of terminology for the rest of the course. So basically, usually, if you take a regular structure of like a Hex mesh, you can see that every face has two axes, right? A face is shared by two different cells. In this case, cells are cubes, also called hexaedral cell or axis in this course. And then you can also have 4 axes for 1 edges, obviously, as you can see here. And if you consider a vertex also, you basically have 8 axes adjacent to a given vertex. So when you have this configuration, you call this configuration regular, right? This is the classical lattice decomposition of the 3D space and the regular tessellation of 3D space. So, but this is not the only case, right? Because Hex-mesh can be complex. They have to align to boundary constraints or to a certain mesh. So you need to insert also irregular vertices. We'll see it later. So here there is an example of irregular vertex or irregular edge, in this case in red, where an edge is shared by 3 axes, right? And each vertex is adjacent to 6 axes. If you consider also another 3 axes on the top of this one, you're gonna count to 6. And this is another irregular configuration that you usually see in hexaedral meshes, where an edge is shared by 5 axes, right? And the vertex is shared among 10 axes. And this is called irregular. So as you can see here, these configurations are called regular or irregular, but sometimes we call this configuration a singularity. And we will see it later because they correspond to specific configuration of a field, of a volumetric field that induce this tessellation. So as you can see, like you can vary the number of axes adjacent to an edge and the number of axes adjacent to a vertex, but usually the number of axes adjacent to a face is always 2. Well, this is true, and when it's true, actually we call the mesh conformal, but it's not always the case. There is some algorithm that cannot guarantee conformality of the mesh, which is a very strong And it's a big desiderata, right? And it's something that most of the algorithm works with HexMesh. They need to have conformal meshes. But there are other algorithms that actually are not conformal, and you can have like one phase which is shared among 3 or more hexas instead of just 2, or 1 in case the phase is on the border of the mesh. So, okay, so we saw the singularity. So having the singularities, you can construct a singularity graph. Singularity graph is a set of edges that are interconnected within the volume, and they often arrive to the surface, to the exterior of the mesh. And here you can see that you have like a singularity of valency 5, and you have another singularity of valence 3. And all these are connected to create a singularity graph. Why is important the singularity graph? We'll see it later on in many contexts it's used, but one of the important things is that it's a good indicator of the internal complexity of a mesh, right? And how it's structured. For example, if you have a nicely structured mesh, like here, one on the left, you have a simple singularity graph where you have these lines and they mostly follow the shape and the semantics and the structure of the object. While when you have something completely unstructured, like the one on the right, which is derived with a grid method that we'll see later on, you have a lot of irregularities, and even the structure, internal structure, is complex, and also the graph shows the complexity of the mesh itself. So given the structure and of the singularity graph, you can actually group a block of regular tessellated elements into chunks, and this is called block decomposition. Here you can see like a first block, a second block, and then you can imagine other blocks, and these blocks are bounded by singularities. And sometimes also this is an important indicator to show the complexity of the mesh. And it's also important for some other applications, like if you want to do multi-grid resolutions in PDA, like solving problems, but we'll see that later. So given these like intuitive measures on the complexity of the mesh, we actually define this HexMesh classification that follows another quad mesh classification from a previous survey that has been published. But we can actually have a regular mesh. A regular mesh is basically one block, right? And you have 8 irregular vertex on the corners. Or you can have a semi-regular, where you have, for example, a few singularities that are there to basically take in consideration to adapt the shape of the mesh to the geometric constraints. Usually this is the best one that you want because it has a nice structure, and it also has a block decomposition. At the same time, it approximates very well the external surface. Then you have valence semi-regular, which is something that tries to be as a semi-regular, but still is not right in that shape. For example, you can see this sort of separatrix, this sort of lines that are emanating from the singularity on the surface. You have some near miss, right? And in the end, you're not going to have this solid, nice black decomposition. And finally, we have the completely irregular mesh, which is good and also sometimes can be used, but you can see that there is a lot of irregularities. And that's the final part of our classification. Basically, moving to the most regular to the most irregular, it's actually you have more irregular vertices and more blocks. So what is the better trade-off? Well, it depends about the shape, right? If the shape is complex, right, it will need more irregular vertices and singularities internally and externally to adapt to the geometric constraints. That's more or less like the same kind of intuition that you have for surface quad meshes, where you have to insert singularities in strategic regions. So I would like to say that, in my opinion, semi-regular are always the best one in general. Okay, so we can define the dual structure also of an Hex-Mesh. We'll see that will be useful later when we introduce the methods. So to explain dual structure of an Hex-Mesh, let me start with the quad mesh, right? So first, in a quad mesh, you have the primal, right? And in a primal of a quad mesh, each face is a quad, and then vertices can have different valencies. And here we also have singularities on the surface, not within the volume, obviously. And actually, if you do the dual of this quad mesh, you generate a set of polygons, and each face, in this case, can be a general polygon. So instead of being just a quad, it can be pentagon or triangles, but vertices have always valence 4. So let's try to have the same kind of translate the same kind of principle into a hex mesh, and you will see that we have similarities. So in the primal, each cell is an X, it's an X cell, so it's a cube, but vertices can have different valences, right? And also edges, as a consequence, can have different valence. So you have edges like singularities that are shared by 3 cubes, and you have edges in regular lattices tessellation, which are shared by 4. Now, in the dual, instead, each cell can be a general polyhedron. So in this case, it's a prism with a triangular base. You can also generate the dual by considering the centroid of each cell, of each cube cell, and then interconnect them among adjacent face, exactly as you do for quads, passing from face to face through the edges. Here you pass from cube to cube through faces. So in this case, each cell is a general polyhedron, but all vertices have valency 6, right? So, and all edges has valency 4. So this is good for some approach to base their meshing strategy, considering this property of the dual structure. So you can see like a dual of a regular tessellation, right, and a dual of a tessellation with a singularity, that you can see that now we have a prism cell in the middle. So when you have a dual, we'll have some kind of these planar slides that are called sheets, right? And then you can have chords if you actually follow these lines along the direction of the primal tessellation, okay? So these are some kind of terminology that people use into dual. So right now we talked about structure, dual, singularities. Another important characteristic of Hex-Mesh is the quality. So we want to assess the quality of an Hex-Mesh as how much an hexahedra deviates from the ideal cube having the same volume. That's the intuition, right? So I don't want to go too much into detail on that, but good quality is very important for most of the application we'll see later on. And sometimes elongated hexahedra are also okay if they are aligning with the curvatory direction. So I don't want to go into detail, but there is a lot of different quality measures. Some of them, they are more tolerant with respect to elongated. Some of them measures other kind of characteristics of the cell. Usually, people relies on the Jacobian, right, or the scaled Jacobian. So those are the more common measures used in literature, but there are many others if you want to visualize different kind of aspect of the cell. So this is the set of measures that are actually implemented also into XLab. I will see later. So, okay, so right now we talked about structure and as well quality of hexahedral element, but I haven't talked right now about why these hexahedral meshes are important, right? So, well, hexahedral meshes are the optimal domain for solving partial differential equation, right? And we will see that there is a lot of cases in industry, right, and in research where people have to solve PDE, for example, to simulate the fluid or to simulate aerodynamics of a car, or to, for example, in the aerospace industry, to simulate like the aerodynamics of an airplane, right? So you basically embed your 3D mesh of the airplane into a tessellated surroundings, right? You can actually estimate the velocity for each point and the pressure of the flow everywhere. And also in naval industry, right, it make a large use of these meshes to simulate flows and to have particular kind of effect like turbulence, or simulate that for designing some kind of particular shape of turbine, or any kind of object that is immersed in a liquid and has a certain velocity or make a certain movement. Obviously, the most classical application is like stress analysis. So you basically have some 3D object you want to discretize in some way. So hexahedral are nice in some way, and sometimes also tetrahedrals are, or more often tetrahedral are used because they are easier to achieve. We will talk about later about the difference between hex meshes and tetrahedral meshes. That's not the main topics right now. Also, there is people who try to use this, and they found very interesting use of Hex-meshes for biomechanical analysis. This is one of the best application of Hex-meshes because respect to tetrahedral mesh, they don't suffer of the blocking issues. So an Hex can actually deform more before it can actually invert the volume. So it works maybe better in general to simulate very deformable tissues and with large deformations. So that concludes the first part of the introduction, and we'll go to see how the structure, how the course is structured. Hello, and here we show an outline of this course. First, we actually already seen an intro of the structure of the Hex-Mesh, and in local, like singularities, and global structure, like singularity graphs and how blocks are organized, and the classification of different meshes, and also like the applications of X meshes to real-world engineering problem. Then Marco already shown you some talk and discussion about what are the desiderata for some meshes, in this case, like geometric approximation or block decomposition or geometric feature, whatever you want to actually achieve when you actually create an Hex-mesh from usually a surface mesh. And then we'll talk about different methods for Hex-mesh generation. So there are several methods that has been proposed in this schedule. We make an overview of all of them, not going too much into details for matters of time, obviously, but we'll start with the advancing front methods. Then we will talk about the dual approach that exploits the dual structure of Hex-mesh. Then we'll talk about domain decomposition, so how you can split, right, the surface into different patches, and then use some predefined tessellation to assemble a Hex-mesh. Then there are the most robust methods, which are called grid-based methods. We'll see advantage and drawbacks of these methods that are commonly used in industry, and some new methods, including polycube maps. So like this bunny here that has been mapped to a polycube and used to create these volumetric hex meshes. And the new methods based on frame field, which is a set of vectors that actually identify the main directions of the axis within the volume. So these are the most new methods. But also there is other methods that gained a lot of success that try to relax the constraint of having all X meshes, and those are called X dominant meshes. So meshes where most of the elements are hexahedral, but you can have other elements which are not. And though we will talk also about this X dominant. Then we will talk about tools for the visualization of X meshes, because sometimes, like when you create an HexMesh algorithm and you want to assess, obviously sometimes you spend a lot of time trying to visualize the structure, the internal structure. You have to write some software, but there are some tools around, as there is some solution that has been proposed in the last year that would be interesting to explore. That's why we also added these parts into our course. And finally, we will talk about what are the future challenging, right, and bit of reflections. And so there will be also some time for questions in the real talk at SIGGRAPH. So we'll talk about different kind of aspects that current methods lacks and that can be improved in the near future.
Okay, so output hexahedral or X-dominant meshes are expected to fulfill both topological and geometric requirements. In particular, topological requirements are about the mesh connectivity, so how the vertices are connected to one another to form the volumetric cells. And the geometric requirements are about the vertex coordinates, so the XYZ coordinates, which is what we typically call the embedding. So let's see first the topological requirement. Given a mesh like this one, which is X-dominant, we distinguish between regular elements like hexahedra, which are composed by 8 vertices, 12 edges, and 6 quadrilateral faces, and what we call hybrid cells, which are non-hexahedral cells, in this case, a triangular prism that is composed of 6 vertices, 9 edges, and 5 faces. So hexahedral dominant meshing algorithms tend to produce volumes which contain both types of elements. And we don't have to think that the elements are always this simple. Depending on the algorithm, elements can be much more complex, like in this case, in which polyhedral agglomeration introduced a single volumetric element, that is the one in red, which is composed of 44 vertices, 83 edges, and 41 faces. So depending on the methods, the complexity of these elements can vary a lot. And so a natural question to ask is there unlimited freedom for hexahedral dominant meshing methods in order to introduce any type of volumetric element? And in reality, the answer is no, because the mesh topology must be compatible with the PDE solver that we intend to use to solve the PDE on the mesh domain. There are many different examples. Here I'm going to mention just one, which is related to the polyspline method proposed by Schneider et al. In 2019. And this specific PDE solver supports non-hexahedral cells only if all faces of the cells are quadrilateral faces. And in the paper, they describe, for example, a procedure that through midpoint refinement is able to always fulfill this requirement at the cost, of course, to increase the resolution of the mesh due to the refinement step that is applied. Another important metric for hexahedral dominant meshes is the amount of non-hexahedral cells, which must be as low as possible. And this is because many times PDE solvers tend to introduce additional vertices surrounding the non-hexahedral cells in order to fit the functions through which the solution will be represented. And so the fewer hybrid elements we have, the fewer additional degrees of freedom we will have in our linear system. The authors of Loopy Cats in 2020 introduced this naming for strongly hex-dominant meshes, which are essentially meshes, or essentially denote a meshing algorithm that in the 80% of the cases produces a pure hexahedral mesh, so no hybrid elements at all. And in the remaining 20% of the cases, it produces hybrid cells just for 2% of the overall number of cells in the mesh, so quite low number of non-hexahedral elements in the mesh. Another advance in this field comes from a more recent paper by Buchenberg et al. In 2022, so already this year, in which the authors define what is called an at most hexa mesh, which is essentially a mesh in which every single element is guaranteed to restrict to a very specific category of solids, which are all the solids that can be constructed by starting from an hexahedron and collapsing an edge or a face. And in terms of topology of every single element, this means that every single element will have no more than 6 faces, because 6 is the number of faces of an hexahedron. And every single face will have no more than 4 sides, because the faces of an hexahedron have only 4 sides, and we are just modifying them through collapsing, so simplification essentially. Not only the type of the elements, but also the way these elements are assembled together in the mesh may be subject to restriction by the PD solvers. And this is what we refer to as the local topology of the mesh. Taking again the polyspline fan method as an example, these particular solvers put restrictions on hybrid cells in the sense that these hybrid cells cannot be adjacent to one another in the mesh, and they also cannot be exposed on the boundary. And these two properties, as the authors explain in the paper, were guaranteed in this case by applying what is called the polar refinement, which is depicted here in the bottom right of the slide, in which essentially a point in the kernel of this polygon, or you can imagine polyhedron in 3D, is connected with the vertices, and then sort of a padding layer is introduced within the element in order to make sure that if it was adjacent to another hybrid element, and now there are 2 separation layers, one for every single element. Of course, this type of procedure implies that the elements are star-shaped, so the kernel of every single element must be non-empty. And other solvers may have other requirements in terms of the local topology of the mesh. Not only the local, but also the global topology, or what we call the coarse block layout or coarse block decomposition of the mesh is very important, mainly for 2 reasons. First of all, well-structured hexahedral meshes can be stored and queried more efficiently because we can take advantage of the fact that in most of the places, the mesh looks like a regular grid, and so we can efficiently encode the adjacencies and the way we compute quantities because of this kind of standard regular connectivity. And the second reason is that these structures are actually useful for methods like isogeometric analysis, because in every single domain, we can fit a tensor product, spline basis, and we can use this coarse block decomposition to solve our PDE. Now, in terms of ability to produce a coarse block decomposition, as we will see next in these presentations, different methods behave differently. For example, of 3 methods tend to produce extremely unstructured meshes in which the domain decomposition contains as many domains as the number of elements in the mesh, and methods that produce more structured meshes, for example, loopy cuts and polycube methods, frame field methods, as we will see, tend to produce a number of domains which is much lower with respect to the number of elements in the mesh, which is a good property for, as I said, ad hoc data structures and for IGA methods. Other important property, topological, is mesh conformity. Mesh conformity is essentially a topological continuity between adjacent elements which are supposed to touch through entire faces, edges, or vertices. When this doesn't happen, like in this picture, you may have, for example, an hexahedron and the face of an hexahedron which is shared between 2 adjacent elements which are just partially overlapping with this quadrilateral face. Many X-dominant methods that operate through agglomeration produce meshes of this kind, for example, the PGP3D method proposed by Sokolov et al. And these methods are still useful to solve PDEs, but they require special solvers that are able to propagate and compute the solution on these topological structures. For example, this continuous Galerkin is a very popular solver that is suitable for this type of meshes. And in some cases, special topological connectors can be used to provide the topological continuity, so the mesh conformity. And these are typically 0 volume elements that are just put in between the elements in order to, at least from a topological perspective, provide the wanted continuity. The geometric properties start with the most basic one, which is the geometric fidelity. That is the ability of our volumetric mesh to faithfully represent our target geometry. And of course, this is something that depends on how many elements we have. The finer the mesh, the better the accuracy with which we are representing our target geometry, as you can see in this image. Another important, especially for CAD and industry applications, property is the ability to preserve the features, which means that all the sharp creases of our CAD designs must be endowed in the connectivity of the mesh, meaning that the hexahedral elements or the edges of the hexahedral elements must be aligned with these features, like you see in this close-ups. It is important to remind that the features are not only geometric ones, like sharp creases, but can also be semantic ones. A typical semantic feature could be, for example, the separation between different materials in a composite object. And in this case, from a geometric point of view, you may not see anything, but since you want to simulate and to attach different materials to different elements of the mesh, you still need to be able to provide a separation between the elements that belong to one material and the elements that belong to the other. So this is another feature that is very important for meshing algorithms. The element quality is very important as well, because the simulation accuracy mostly depends on the shape of the elements. In the case of hexahedral meshing, the ideal element is a perfect cube, and any deviation from a perfect cube implies some sort of loss of accuracy. And in particular, a measure that is always important and is like the minimum requirement for a mesh to be usable for simulation is that the scale Jacobian of the mapping between your element and a reference element, for example, the perfect cube in the case of hexahedra, must be positive everywhere. And even the presence of a single imparted element, so an element for which the scale Jacobian is below 0 at some of its interior or boundary points, makes the mesh completely unusable for simulation. So this is a minimum requirement. In addition to this minimum requirement, there is a whole bunch of shape regularity criteria, which are necessary to ensure that the PDE solver provides optimal convergence. And in particular, in the theory that mathematicians have developed, the error bounds for the various solvers are linked to geometric quantities that are associated to the elements of the mesh. For example, the diameter of the shape, which is the ratio between the outer and inner circle, the angles, the sides of the kernel, the number of the sides, the edge lengths, and so on and so forth. So meshing algorithms are required to provide, depending on the solver with which they are coupled, elements which are good with respect to one or a subset of these metrics. Now, it is important to remind that actually there is no free lunch, in the sense that existing Hex-meshing methods can hardly address all these requirements. It's just too complex is a problem that is too complex to be attacked altogether. And so if you take a look at the literature, you will find out that most of the methods focus only on a small subset of the geometric or topological criteria. For example, they can guarantee that the elements are hexahedra, but then they no guarantee the topology, so the singularities of the mesh or the quality of the elements, or maybe they put guarantees on the singularity of the elements, but not on the quality, or they can provide like geometric guarantees in terms of feature approximation, shape preservation, but they do not provide guarantees in terms of topology. It's always a trade-off between these various metrics. And a very practical solution that is used pretty much everywhere is that any type of property that is relevant for the problem to be solved and is not endowed in the mesh by construction by the solver can actually be attacked and ameliorated in post-processing. And we will see during the rest of the course some of the techniques that are used to improve both geometric and topological qualities of a given mesh.
Okay, welcome back. Now we'll talk about the first method for Hex-Mesh creation, one of the first that has been proposed in the literature, which is advancing or receding fronts. So maybe some of you already is familiar with methods called advancing front, because it was a method that has been used a long time for creating triangulation or tessellation in general, for tessellating 2D space, or to tessellate also like 3D space. We'll see right now how we can use it to some kind of the same ideas to tessellate surface, like volumes. So the idea, the basic idea of advancing front method is start with a boundary where usually sometimes you have already a set of predefined discretized constraints, like position of vertices. And in the case of the triangulation, you tessellate by propagating the boundaries from the outside to the interior. So, and here you have several solutions. For example, you can just propagate a triangle in the interior, but you can also several options. For example, you can consider also how you change the topology, right? How you change the connectivity or the interconnectivity between vertices. For example, you can actually only add one edge that connect two triangles that are already in the border and close a sort of a very convex angle. Or you can add a vertex in the middle, for example, that connect these different four vertices and insert three triangles at a time, maybe more desirable in some kind of heuristic choice of what is the best next move. You can also link to different fronts, or you can also like create a triangle to close a hole, right? If the hole is a triangle directly. So this, it tends to be kind of stable with triangles, but with quads, it's tricky, right? Especially the problem is like what you do when two different fronts meet. So then there is several algorithm proposed in literature. You can distinguish between constrained, so the one that has the boundary which is constrained by a set of already having a tessellation, or unconstrained where you don't have any vertex, right, predefined on the boundary. So this translates basically in Hex-meshing. If the boundary is already quadrangulated and you want to have your hexa to conform to this quadrangulation or not, and for example, you start with a simple triangle mesh. So one method that we want to show you is this unconstrained paving. So the idea is like you have a set of class of shapes that have a set of degrees of freedom in the way they can be tessellated. For example, you can have polygons that can be tessellated into different directions along the U and along the V by changing the number of subdivisions, right? You can actually have strips, so you can change the number of subdivisions along only one direction. In this case, along the height of this strip, or you can have also shapes with like intervals or parts of the areas where you have 0 degrees of freedom. So first of all, I want to introduce this one because this works in 2D. Then we'll see and try to have an intuition about how this works in 3D. So I actually suggest you to see the related paper to have more details about that. So then you actually can start having something that has 2 degrees of freedom, like this big mesh, and you can start tessellating, like advancing the fronts on the side. So you can say like, oh, you know what, I can propagate this side. So then I have something that has 1 degree of freedom, so I can only decide how to tessellate along the Y. So you can do the same in the other direction. So then at the end, you're going to end up one particular green cubes that has no more degrees of freedom. So because it's the intersection of 2 different advancing front with 2 different degrees of freedom. So then you can repeat that until you basically tessellate the entire mesh, right? And then you can use an inverse, and this is the case of 2D. We'll see also in 3D the intuition, but it's easier to explain in 2D. Then you can basically say like, I know that this has to be quad or hexas in this case, hexas or quad in this 2D case. So then I can go to the next one and I can say, oh, I know that this has to be 1 by 1. Then I can take the next one. This has more degrees of freedom. And I can define how to tessellate these. And because this has 4 edges, right? I can tessellate with a simple 2 by 3 tessellation. And then this one expand to the neighbors, which are 1 degree of freedom, and then induce tessellation to the neighbors, and so on until you basically tessellated the entire area. So if you consider how this works in 3D, it's pretty much similar. You have to basically expand this front. And that's a very tricky part because if you don't have any particular guidance, you have to rely on geodesic or like 3D information or some volumetric field. somehow, and then you can continue like expanding this front altogether until you get a fine tessellation, for which you also have noticed that here, with respect to the 2D case, we also have like cells that has 3 degrees of freedom, right? Because we have more dimension. And then you can end up with some predefined polyhedra that you know how to tessellate, and then you actually propagate the tessellation on the neighbors, trying to satisfy all the constraints. So there is also another kind of approach, which is called receding fronts, that has been proposed. The idea is like to combine sort of a geodesic from outside of the surface to the inside of the surface, and have this kind of function, geodesic function, that you can cut along orthogonal lines to get finally the tessellation. So these methods are, in line of principle, easy, but in the end they realize, but in the end they really complex to achieve robustness for many issues, like, for example, how do you propagate these sheets within the volume, right? So if the volume has a certain complex shapes, that's not easy. More than that is like you have issues with robustness. Maybe you can have some of these sheets which are really close to each other, right? And maybe you want to snap to a certain other sheets, right? Because you don't want to create millions or tons of small elements when two actually sheets, they almost intersect each other. Here we have 2 examples. And these advancing fronts methods, they use some of the trick to actually snap these fronts, but it's it's not the most robust technique. Okay, so another class of methods for HexMesh creation are called dual methods. So they basically exploit the fact that and they work in the domain of dual meshes. We have seen already what is the dual of an hexahedral meshes. Is something where you basically can imagine to connect the center of its axis with the center of adjacent axis, right? And so you actually create this sort of a structure where you can have these chords and sheets. So even in this case, we have unconstrained or constrained methods. So let's see a bit of constrained method. Basically are the one where you have the boundary already defined in terms of quads that you have to match. So let's recall what we said at the beginning, that we have sheets and chords, right? Sheets are this kind of main layers that are in the dual meshes, and chords are sort of a line aligned with the direction of the axis into these sheets. So why this is important? Because some of the dual advancing front that start with the quad meshes are based on chords, right? You have to perform this operation on chords and simplify these chords in order to have like a final Hex-Mesh. So the idea, you can actually analyze how these chords are on the original surface, right? You can see that the black lines are the primal, and these chords, like they show red, green, and blue, they show the dual, right? And then you can use some kind of operation that lead to the creation of axes, and then you propagate these chords into the interior. For example, if you have this configuration here on the top, right, you can actually transform to this other configuration where the chords, like they are interconnected in a different way, and this leads to the creation of an hexa, right? But you can also have some other operation that eliminate this sort of small dangling surface parts, which happens during this greedy algorithm, Or you can have also other operation that takes parallel lines or of cores with another vertical that intersect and change the configuration, leading to the creation of another hexagon. Obviously, there are also some other more complex configuration where these nested loops of chords, where you can actually split the loops and also lead the creation of a new axis by considering this graph of chords. So, well, this works somehow good, but always depending on the external meshes, right? If you have different like tessellation of the external mesh, the method can non-converge or converge to some very bad meshes. So they're highly dependent on the external tessellation of the quad mesh that you start to create these chords. There are also another kind of method which are called unconstrained, and we will see some of them. So basically, they are based on this idea that you have somehow a guiding field, or can be guided by the user, but they are built on this idea of this paper called dual loop meshing, proposed by Marcel Kampen and colleague, where you want to create this set of loops, and you want to have enough loops such that you can dualize this set of loops, and you can have a set of cells on the surface that when you actually take the primal of this setup, you're going to have quadrilateral patches like this one show. So you find the loops to create a dual decomposition, then you actually do one subdivision step, and you get, or you dualize, and you get like the quad patch layout that you can use to create the quadrilateral meshes. Okay, so some of these methods, they follow the same principle, and the game is like how you can distribute this kind of loops, this kind of structure to split the mesh into different parts. So for example, Takayama and colleagues, they use like a manual things, because they say like how we can generate enough sheets to split the object into different parts, right? So the idea is like you can take a mesh, define a set of sheets that also consider the features of the object, and then you dualize and you get your hexahedral meshes. So, okay, let's first consider what happened in primal and dual, right? So if you have like, that's just a bit of theory and a bit of reasoning of what's going to happen. If you have a singularity, like a valence tree singularity, that will induce in the dual a tetrahedral cell, right? And you can actually encode this one as 4, 0, 0, where the first one is number of edges of valency 3, number of edges of valency 4, number of edges of valency 5. So we omit valency 2 and 6 and more because they're not very useful in terms of 3D modeling of shape, but may be possible for very like extreme case, but not in this case. So then in the dual, you basically have something similar, but you can express the number of triangles, quads, and pentagons, right? Or yeah, in this case, it's like the number of face that are triangles, number of face that are quads, and number of face that are pentagons. In this case, is a tetrahedron, so you have just 4 triangles. So this is similar. In this other case, you have a prism which is like a valency 3 edge, right? And this goes to the dual to a prism that has a triangular base, right? And then in general, if you assume that every edge valency is between 3, 4, 5, and every face every face is a triangle, quadrilateral, or pentagon, then all vertices, they goes into this 11 types of topology, and then you can have in the dual 11 type of polyhedra. Right here, I show only 10 because there is also the classical tessellation of like regular lattices. So following this intuition, like Takayama and colleague, they created this structure that make this interactive decomposition and taking care that you always preserve this kind of dual structure when you cut, and the user has to create this cut manually on the mesh, right? And then as a consequence, the surface is split into multiple polyhedral until some of the configuration are matched. So this is the approach by Takayama colleague. The results are very nice, and you have a nice block decomposition, but it's manual, right? So, and obviously there is some particular challenging implementation details, such that how you propagate or how you split internal tetrahedral elements to create your mesh. So always consider that when we actually talk about Hex-meshing, sometimes we start with a triangle mesh. Most of the methods start with a tetrahedral mesh, given the fact that it's much easier to derive a tetrahedral mesh. We don't need a super good quality tetrahedral mesh, but it's better. Some of method requires already a volumetric like domain, like this one. So there is another possibility, is this paper proposed by Marco and myself and colleagues in 2020, SIGGRAPH. Is automatic. It's called looping cut. The idea is like to look at the object and then decide how to split, right? And split many times, right? Until the object becomes meshable, right? So these polyhedral like cells, they match the constraints that we actually defined before. So you can actually split, and you can subdivide and get like atomic mesh, like you can get an Hex-mesh. So the idea is like, first of all, the problem is like how you split, right? So how you distribute these loops, right, on the surface, and then how you can perform this volumetric cutting that we use a volumetric function to define where to place the cut. So we defined a very effective method to distribute loops on the surface, which is based always like define what is the best options, right? And try to distribute the fastest with respect to the previous one in the space of loops. You can have details about that distribution in the paper. Obviously, if you have feature lines, you have to manage particularly because you have to split this mesh into concave feature that will propagate inside the volume, and they split the mesh into different parts, as you can see here. So, and they can split into different directions. So that's it's a very challenging, particular managing of sharp features, and also as a challenging parts of the implementation regards how you basically cut the mesh and the volume using these loops in the interior that we use some function and we propagate this function into the interior, right? And then how we cluster the elements to get this prism or this hex, right, from the decomposition that will be processed with the midpoint refinement to get the final output meshes. So here's the set of results. The method works really well. In this case, one of the most powerful dual methods, but in the end, sometimes it can introduce an hexahedral cell. So it's almost all X, but there are a few non-X's there. Okay, so now we talk about domain decomposition, or another way to create X meshes. So the idea of these meshes, one of the first idea was to decompose the surface into block by using the features on the surface, and then create some sweeping plane where you can actually take one of the plane, right, and propagate through all the volume by and create the tessellation through this sweeping plane. They have to match one to the other across like common regions to make tessellation conformal. So one of the most advanced method for this is like try to estimate what are for different direction and different part of the object, what is the best sweeping plane direction by testing different direction. In this case, you can see the colors and the sweepability, right? How much you can sweep a particular part of the surface along a certain direction, and then recursively construct and optimize a set of cutting phase. So, and then you can split the object into different parts so that you can basically get the right decomposition and sweep this plane in a certain direction. So this approach has been proposed by Wu and colleague. And you can see that also you can split an object multiple times in an hierarchical fashion, right? It also gives you like this particular decomposition. So it works kind of decently with and nice with like man-made object where most of the faces are aligned with features or with like axis direction, but when you have organic shapes or much more complex, it doesn't really generalize for most of them. So you can also improve these methods, use some topological condition or geometric condition to be more general, like this approach by Wang and colleagues, right, where you can define the sweeping planes using like more topological and interconnectivity between them. So another possibility is this medial descriptor. So suppose you have a 3D shape like this organic armadillo. So what you want to obtain, a skeleton with the tubular structures where you have already the topology inside and the connectivity inside of the cube inside these meshes. And then you can basically massage and project this tubular structure on the final surface and tessellate as a consequence to obtain a mesh composed by hexahedral only. So this approach has been proposed by Marco Liveso and colleagues into different forms. The first one doesn't take much into consideration of conforming to the boundaries, and the last version it conforms to external boundaries, so introduce less singularity and works sensibly better. So the idea is that you can start with a like a surface mesh and a skeleton, and the skeleton has a particular nodes, for example, terminal nodes or junction nodes here in red or in green, and then for each one of them you have a particular tessellation, right, depending on how many branch they connect, right, or if it's a terminal node or not. And then simply you actually have a predefined tessellation for them, and you have to make it consistent along the entire mesh. So you have a small optimization problem that transforms this block structured HexMesh into, I mean, in this case is already coherent, right? You can just subdivide, but you can also decide to subdivide differently for each of the direction of the cube. So this works kind of nicely for structured, organic mesh, where skeleton already define the structure and the semantics of the surface, but obviously it cannot be generalized to any kind of mesh. For example, mechanical mesh with sharp features and so on.
Okay, so let's talk about grid-based approaches. So industry-wise, grid-based approaches are very important because as of today, they are the only existing method for black box hexahedral meshing. What does it mean? It means that they are the only method that is capable of meshing any type of input shape, regardless of its complexity. There is no other method in the literature that can do that. In this field, the theoretical breakthrough is the dual method approach proposed by Maréchal back in 2009 that was firstly encoded in a commercial product called MeshGem and used in the industry. And very recently, this tool was acquired by Dassault and included into the 3D Precise Mesh toolkit. So it's something that is still very relevant in the industry. Let's start from the very basics. So uniform versus adaptive. Let's say that this is kind of the shape that I want to mesh. And I'm going to start with a uniform grid like this. And my mesh initially will be the set of elements in the grid that are internal to the shape. So 16 cells. This is a very crude approximation. So if I want to make it better, I need to uniformly refine my mesh. And in 2D, this is a growth that goes quadratically. In 3D, it goes cubically. Now I have a much better approximation. And if I continue and continue, the approximation will get better and better, and the number of elements in the grid will grow, again, quadratically in 2D and cubically in 3D. If I go adaptive, I will start with a very coarse grid. And again, the number of elements in the interior will define my initial mesh, and then I keep refining only the elements which are crossed by the boundary. And as you can see, by halving essentially the number of elements in the cell, now I have the same quality or accuracy in the approximation of my shape. And this is very important because essentially it means that now I'm decoupling the element size from the resolution of the mesh. So if I have an object which is like very coarse everywhere and it has a very thin feature that I want to get, if I go for uniform meshing, the size of the grid is gonna depend on that thin feature. And so the mesh is gonna be huge, maybe unbearable for my computer. If I have an adaptive grid, I can adaptively refine only there where the feature is. And so I will save a lot of memory and become much more efficient. So that's why adaptive methods are used. Anytime we talk about adaptivity and refinement of the grid elements, in the literature, we find mentioning two types of refinement, 1 and 2 refinement. Assuming that an element is 0 refined, applying 1 refinement means that I'm going to split every edge of my cubes once, and this produces a subgrid of 2 by 2 by 2 elements. So an adaptive grid that is done in this way can be encoded in an octree because every coarse element will have 8 children, like in an octree, right? If I want to apply 2 refinement, it means that I'm going to split every single edge in my element twice. And so this produces a subgrid of 3 by 3 by 3. And in this case, if I want to encode this kind of adaptive mesh in a tree, the tree is going to be a 27 tree. Now, for some reason in the literature, this is not well explained. And if you read papers that in the field, you will find that everybody mentions octrees, regardless of whether 1 or 2 refinement is used. And so I'm taking opportunity of this presentation just to say that anytime you read octree in this field, you need to interpret as a vague term that intends that you're using a tree representation for your adaptive grid, but then depending on the type of refinement, the tree is going to be an octree for real or a 27 tree. Okay, now let's go back to our adaptive grid. It's very nice that we have halved the number of elements, but now we have a problem because all these kind of orange points are what we call hanging nodes. So are points where we are breaking the conformity of the mesh. Now we have, these points are essentially at the midpoint of long edges that belong to coarser elements in the grid. And if you want to make a conforming mesh, we need to suppress them, incorporating them in the connectivity. So that's the major goal of grid-based literature. There are mainly 2 ways to approach the problem. One is what goes under the name of primal methods, and the other one is dual methods. I'm going to cover the primal methods first, and the main idea here is to incorporate the hanging nodes directly into the grid connectivity. So I have a coarse element and an hanging node because it is touched by 2 finer elements. And the way to incorporate this hanging node into connectivity is by splitting into 3 sub-elements this coarse one. Now, as you can notice, I have this outgoing line, which has to go somewhere because it's splitting the boundary of my quad. And in fact, this is a scheme that spans 2 alternative cells. So I need to have another one where I applicate like the specular of the same scheme. This is for the case of 1 refinement. On the other end, if I have 2 refinement, I have 2 hanging nodes that are insisting in the same element, and so I can apply kind of the same topological bridge inside a single element. And this is local to a single cell, so it's much easier to implement and to handle in terms of data structures. And that's maybe one of the reasons why the literature in primal methods is mostly working on tool refinement of grids. Now, the problem of all primal approaches, regardless of whether one or two refinement is used, is that some configurations cannot provably be covered, because in the concave corners, if you consider the boundary of the cells that you would like to, in 3D, transform into hexahedral elements, is covered by an odd number of quads. And there are theorems that show that if you have a surface of quads composed of an odd number of quads, it is impossible to fill that volume with hexahedra. A condition for which a solution exists is that the number of quads in the outside is even. And this was proved by Michel and Thurston in 96 and 93. And this essentially kills any hope that the primal methods can do it all. So there will always be some configurations where these methods are not able to suppress the hanging nodes. In reality, these methods were used anyways, and the way they were used is essentially anytime they could not suppress the hanging nodes, they kept refining and refining until convergence, so introducing a lot of unnecessary additional refinement. These methods were superseded by dual methods in 2009 when they were introduced. And dual methods are based on the intuition that primal vertices in the grid will become cells in the dual, and there are nice topological relations between these elements. In particular, in 2D, there is a dual relation between vertex and cell, meaning that a vertex with n incident edges will become a face with n sides. And in 3D, there are two dual relations, one between vertex and cells, so a vertex with n incident edges will become a cell with n faces, and a face with n sides will become an edge with n cells attached to it. And so if we now think about what are the conditions for the generation of an all-quad or an all-X grid, for 2D, all we need to ensure is that the valence over the vertices of the grid is 4, because then when you dualize, you get quadrilaterals. And in 3D, you need to make sure that the vertices have valence 6, because these will produce cells with 6 faces. And also that the edges have valence 4, because these will produce quadrilateral faces. So cells with 6 quadrilateral faces will become necessarily hexahedral. So that's how these methods work. And the nice thing is that any possible configuration included concave corners that were impossible in the primal methods can now be handled with this dual approach. In 2D, the method works in this way. The metaphor is that you cut your elements in order to regularize the valence. So if you have two hanging nodes like this, they have valence 3. So if you dualize them, you get a triangle. And so what you do is to connect them through an additional vertex that wasn't in the grid. And so the valence of all these vertices will become now 4, such that if you dualize, all these vertices will be attached to quadrilateral faces, which are going to be your quadrangulation of the grid. Note that the footprint of this operation is not local to a single cell, because now we are considering two adjacent cells, and we are suppressing the hanging nodes with a point in between. And this is important, as we will see further down in the presentation. If we take a look at how this extends to 3D, here is a depiction of the transitions. Here we are essentially going vertically from a 4x4 grid to a 2x2. And these are the hanging nodes, these black dots. And the way to suppress them is, first of all, to insert these prismatic elements, this chain here, and then another chain that essentially crosses the first one orthogonally, passing on top of it. And these two chains essentially suppress all the hanging nodes. And what you see here is essentially the topological lead that completes the transition, which is essentially the remaining part of the coarse cells that we cut. Now, ideally, what we see here is two chains that intersect to one another, one passing below and the other on top. And of course, there are two alternative ways to do that. This is the way we have shown here, but also this one is a valid option. Now, for the flat configuration, this is not much important, but if we consider concave transitions, so this is a concave edge, and this is the concavity that we want to use to install our transitions, depending on how these chains of prismatic elements intersect to one another, passing on top or below, we have different configurations. And now this is very important because if you notice here, we have pentagonal faces, which will produce valence 5 edges in the mesh, hexagonal faces, which will produce valence 6 edges, and heptagonal faces, which will produce valence 7. So since valence 5 is a much better singularity, this is the best possible scheme to handle the concave edges. And similarly, you can prove that there is the optimal way also to handle the concave corners. Now, at the end of the day, this translates into a set of 8 atomic bricks that can handle any possible transition everywhere in the grid: concave edges, concave corners, flat regions, everywhere. And this is the primal view of the elements. This is the dual view, front and back. And this is how these elements are installed in order to secure the wanted transition. So dualize this, we will produce an hexahedral mesh. Now the question that one may ask is, now that we have these schemes, is any adaptive grid actually hexable? And the answer is no, because we have 2 main requirements that are necessary in order to be able to install those schemes in the first place. The first requirement is that the grid is balanced, meaning that the size mismatch for 2 adjacent cells must be at most once. And this is a very local configuration because you take an element, you look at your neighbor, and you just check how much refinement they have. There is another one requirement that is called pairing, which says that the number of hanging nodes must be even along all sides. And this is because the hanging nodes will be taken pairwise in order to be suppressed, as you see in this picture. And this is a less local issue, because now you need to be able to count how many hanging nodes you have on all sides, which is not so local. Okay, so if I were to represent the space of all possible grids in the slide, let's say that in the white part, we have any kind of grid. In the blue oval, we have any grid that is fulfilling the balancing criterion. And if you're also fulfilling the pairing criterion, you are in the green oval. So ideally, with the schemes that I presented, I can transform into an hexahedral mesh any grid that sits in the green area. Unfortunately, what we are able to do in terms of imposing pairing is what is called tree pairing, that was proposed by Marshall in 2009 for the first time, which is a procedure that essentially fulfills pairing by refining the tree representation of the grid. And the problem with this approach is that sometimes the grid is already paired, but this criterion fails to notice this property in the tree, and the grid gets refined anyways. That's why, as you can see, the tree pairing region is not as big as the green one, even though the schemes that we know could be potentially able to transform into hexahedral meshes also grids that sit here. So if I have a grid that stays here because this is what my problem dictated and I want to hexahedralize, ideally I'd like to go here, but in practice, through tree refinement, I'm gonna be projected here, over refining my grid. And if I am here, I will be unnecessarily projected here with unnecessary refinement. Now, very recent improvements in the field are the ILP pairing that was proposed by Pizarris et al. In 2021, which substituted the tree pairing with an ILP formulation that allows to find pairing through the resolution of an integer linear problem. And the nice thing about this approach is that now you can cover almost the entire space in the green oval, such that you don't have to over-refine if your input grid was not paired. And another important recent advancement was kind of a relaxation of the balancing criterion, which in the beginning said that elements with more than one level of refinement in the mismatch could not touch in any way, not even at a vertex or an edge. And with this weaker version of balancing, essentially, you can introduce much less refinement. For example, here you have like this cell that is refined 5 times, here 0. And if you impose strong balancing, you get this. And if you impose weak balancing, you get something like 25% less refinement. So it's a lot of saving. And the cost for this is that now you need, in addition to the 8 schemes that I just presented, 5 additional schemes, because cells with 2 levels of refinement will be mismatched, will be touching to one another along the edges, and this has to be handled. Now, combining together the weak balancing and the LP pairing, on average, the size of the grids gets reduced by around 50%. And this seems to be pretty important because just 2 years ago, Ferrari declared that by cutting the number of cells by 15%, so much less, they were able to run 300% more CFD simulations, having like a good aid to produce their cars and design their parts. So this seems to be like a big deal in the industry. Okay, so now we're going to talk about polycube methods. So first of all, what is a polycube? A polycube is nothing but an orthogonal polyhedron, which means that it is a volumetric element in which all the angles between incoming edges are orthogonal, so 90 degrees. The edges are always straight lines, and the faces are always planar faces. So these kind of shapes were introduced in computer graphics for the purpose of texture mapping back in 2004 by Tarini and colleagues. And later on were used also for other applications. In particular, hexahedral meshing is one of the most prominent applications for polycubes. So the idea behind using polycubes for hexahedral mesh generation is kind of to generalize the grid-based approach. So we've just seen that grid-based approaches take an object defined in its object space, let's say, and they apply a grid already in object space to compute the connectivity of an hexahedral mesh. Here, we want to be a little bit smarter. We want to take our shape and just map our shape to a grid-friendly space where making the connectivity of the mesh will be much easier because the mesh actually is aligned with the grid. And so essentially here, the goal is to compute a mapping that we are calling F that takes the bunny and projects it into a polycubization of the bunny. So a polycube space that, as I said, is grid-friendly because as you can see here, if I create a grid on top of the polycube, every single element of the bunny will be actually an hexahedron. So once I have this, I can just take the inverse of my function, and I can use this function, this inverse function, to take every single element in the polycube space and just bring it back to my original object space to compute the final hexahedral mesh. So that's pretty much the pipeline for polycube-based approaches. And there are 2 main difficulties in these approaches. First of all, we need to understand to what polycube, to what orthogonal polyhedron we want to map our shape. And this polyhedron has to be like a faithful representation of the shape that we want to HexMesh. Otherwise, the connectivity that we create in polycube space is not going to match very nicely to the shape that we want to hexahedralize. And the other thing is that once we have decided what is the structure of the polycube, we want to be able to compute this kind of mapping, and this mapping has to be injective because otherwise I may map elements that are disjoint in polycube space into elements that are actually overlapping in object space. And this is something that I don't want to because it's not physical. So the typical approach is to, first of all, define the structure of the polycube through a labeling, or if you want, a colorization of the surface. Here that is that essentially every single color on the surface represent the wish for that point to be aligned with respect to some of the one of the 3 axes, X, Y, Z in object space. And so the charts, which is the locus of points which are assigned the same color, are going to create or define the faces of the polycube. So we start from this kind of definition, which is a polycube labeling. And through deformation, we start to change the shape and to make it more and more aligned to the axis in object space until eventually we get a super nice polycube structure. Now, since we have created the polycube structure through a mesh deformation process, now I have a natural mapping between the 2, because what I've done here is to take this mesh, which is a volumetric mesh, so a tetrahedralization of this shape, and I'm just keeping the connectivity fixed and changing or updating the position of the vertices of the mesh until the mesh is done in this way. And there are 2 versions of this pipeline. One may, first of all, compute a polycube labeling and trust that this is a good one and just keep it until the very end. Otherwise, you can try to be a little bit smart and fix any problem that arises throughout the pipeline and update the labeling during the process. And in this case, maybe you can fix something as soon as you realize that things are not going as well as you wish. Now, as I said, there are a number of structural issues that may arise when you compute a polycube labeling. This is the most typical kind of artifact that you see in polycube approaches. This is what is called in the literature a non-monotone boundary. You can imagine that this gray area is going to be a face of the polycube. This red area is going to be another face of the polycube. And this line is going to be a straight line. So if I make this wiggled line straight, I'm going to introduce a lot of distortion because I'm kind of opening this wedge until it becomes a straight line. And so this is not a good polycube mapping, because then when I compute my hexahedra and bring them back, here the mesh will be horrible. So already in 2011, kind of solutions were computed to address this issue. And the most trivial solution was to apply some sort of template to fix the defect. And in this case, for example, you add a cut here, you have this blue chart, which is going to have a third orientation. And so now you have a step. And as you can see, this boundary here is not adjacent to this one. And this is partly fixing the process. The problem with this approach is that it's completely unaware of the geometry that is behind, because it's purely based on a template that doesn't take into account geometry. There are also alternatives. For example, anytime you have something like this, you can voxelize your deformed or partially deformed shape in order to understand what is the best kind of orientation assignment for this region in order to have a sound polycube. Or you can also apply kind of stochastic approach and optimization, for example, hill climbing, to locally explore the space of segmentations or of polycube segmentations until you find a solution that produces a structurally sound orthogonal polyhedron. So these are the main three approaches for addressing the structural issues in the polycube. Now, this thing of computing a valid polycube structure through colorization of the surface is actually a very complex problem. And as of today, we do not have like a perfect algorithm that is fast, efficient, and guaranteed correct. And the main reason for this lack of a good algorithm is that the validity conditions are not local conditions, but are global ones. And so incorporating them into algorithms makes them extremely inefficient and is overall a complicated matter. So there are some configurations which are widely known to be extremely challenging. And these are, for example, these four here. As you can see, these four structures do not define a valid polycube. And the reason is that if I take this green chart and I imagine to flatten it, this little wedge here in blue will collapse. The same would happen to this little round shape here. It will collapse if I make this green part flat. And here again, I have a face that goes back to itself. And then there is this star that if I make the green part flat again will collapse. So all these structures are not graphs of orthogonal polyhedra. And fixing them will require to do something like this, in which essentially we are breaking these kind of cycles in order to make sure that this part and this part are now not connected to one another and can have different heights in the polycube space. And this is a very hard problem to do, as I said, because trying to understand when these kind of fixes are needed is a global problem. Another important concept in polycube approaches is the definition, is the difference between extrinsic and intrinsic polycubes. So extrinsic polycubes are essentially polycubes that are defined by taking into consideration the orientation of the surface with respect to the global XYZ axis. So for example, these points here are pointing on this right direction, and so I want to place them in a face like this. The problem with these approaches is that when you have a shape like this, which is nice and round, but is just changing orientation with respect to the global axis, you tend to split the structure in polycube space, introducing new elements in the polycube, for example, these corners pointed by the arrows. And the polycube corners are going to define singularities in the hexahedral mesh, which are completely misaligned with your shape and introduce elements of poorer quality because they are not geometrically needed in a sense. So the idea of intrinsic approaches is to kind of do the same approach, but rather than trying to understand how much every surface element is aligned with the global axis, you just change locally if your local neighborhood is nice and happy to stay in the same chart, or if you have some kind of discontinuity and you want to assign different elements in the local neighborhood to different faces of the polycube. And the effect of working in the intrinsic metric is that when you have something like this, rather than splitting, you just unfold your shape and you compute a mapping to a polycube like this, which once you sample it, will provide you elements which are much better aligned with the boundary of the shape. So intrinsic tends to produce much better hexahedral elements for polycube approaches. Regardless of whether you work with intrinsic or extrinsic, the type of pipeline actually doesn't change much, because also in this case, you are kind of working through a progressive mesh deformation process. The only difference is that when you want to be truly intrinsic, rather than computing a global labeling, you start from a seed, in this case, like this little portion with color here. I'm not sure it's visible in the slide. And then you kind of propagate. And as soon as you propagate, you also deform the shape accordingly until you find something which is reasonably close to a polycube structure. And then you apply the final deformation to make it a real polycube. And you overlay a grid on top of it and compute the inverse mapping. But if you do not consider that in this case, the labeling is propagated through time rather than being computed all in advance, the pipeline is pretty much the same. Now, as I said before, in this step, when you move from the polycube to a quantization, what you do essentially is to assign integer coordinates to the corners of your polycube. And this is something that is needed because at the end of the day, you want to make sure that the boundaries of your shape are aligned with the boundaries of the elements of your grid. And this is something that happens only if your corners have integer coordinates. So you want to make sure that the element is either completely inside or completely outside your target shape. Now, depending on how you do this rounding, you may have lots of problems. In literature, the typical approach, especially in the beginning, in the early days, was just to round to the closest integer. And that's why you used to see a lot of super fine meshes, because if your grid is very coarse, you may run into lots of issues like this. So what happened here? It happened that essentially the y coordinate of these points was the same. So they all snap to the same horizontal isoline. And by doing that, they completely collapsed this region. So now if you do a sampling in this space, this region is going to be completely missing because it has zero volume in your integer polycube. So a good quantization is a quantization that doesn't collapse anything, something like this. And in literature, we have seen many papers trying to address this problem. It's actually a challenging problem. Typical approaches were based on integer optimization, but more recently, last year actually, there was a paper based on the construction of 3D motorcycle graphs proposed by Brackler et al., in which they showed that through the construction of these 3D motorcycle graphs, they could provide a coarse quantization of the corners of the polycube that provides a nice and sound structure without any degenerate element. So this is pretty much the state of the art for this particular problem as of today. For the feature preservation, features will be automatically preserved by polycubization algorithms if they map to the edges of the polycube, because the edges of the polycube are always going to be chains of edges in the output hexahedral mesh. However, if you take a look at the literature, there is actually almost no method that takes explicitly features into consideration. The only exception to this rule is this paper from Gu et al. From 2020, in which they proposed this kind of feature-aware polycubization pipeline. And the pipeline works as follows. Well, first of all, they start from the feature, and they try to transform every single feature line, which is a curve in 3D space, into a polyline, which is axis aligned in 3D space. And this is going to be kind of the target position for the feature in the polycube. Then they try to understand which of these curves participate to the definition of a valid polycube and which not. For example, these red curves here are not valid polycube features, and so they are discarded. For all the others, they are used to trigger a deformation process, which is not yet a polycube, but is quite close to it. And on top of this representation, they compute the labeling that defines the definition of a polycube. They use the polycat algorithm, and they check whether along the feature lines that they have retained, the labeling is correct or not. And if it's not, like in this case, they fix the labeling, and then they go for the final polycube deformation, producing a mapping between this shape and this polycube. And so in this case, not all the features, but at least all the features that survive this step are guaranteed to be mapped. One note to this pipeline is that also in this case, the only features that are being preserved are the ones that map to the borders, to the edges of the polycube. But in reality, one could also imagine to map features to inner faces of the polycube and just make sure that the grid sampling that is applied to the polycube actually catches those lines. So they are going to be integral isolines in the parameterization. But this possibility is not explored in the current literature, so there is no method that is capable of doing that. A few words on adaptivity. So we've already just seen something about adaptivity when I talked about grid-based approaches. And last year in 2021, Pizzalis and colleagues showed that what is done in terms of adaptivity on regular grids, so subdivided cubes, can also be done with their schemes into grids with non-trivial topology, like in this case. So you can also be adaptive in the same way on this kind of grids. And in the space of polycubes, adaptivity can become useful for mainly two reasons. The first reason is that you can use adaptivity to improve the fidelity, the geometric fidelity of your mapping. For example, if you go with a coarse sampling of your polycube, you get a nose like this, which doesn't look like a nose at all. If you go to a little bit denser, you get like this, but still it's not quite the shape that you want it to have. And if you go adaptive, you can kind of bound the complexity of your mesh, but still get a nice silhouette for this feature of the max Planck phase. So here you have like positive and negative aspects. The positive thing is that you're improving, of course, geometric fidelity while reducing the impact in the resolution of the mesh. On the negative side, since you're applying a non-uniform sampling in the polycube space, the structure of the mesh is going to be much worse, because now it's not the decomposition of the polycube, but you have lots of singularities that depend on the fact that you are locally refined. And so it really depends on what is the downstream application and what are your goals in terms of output mesh. But it's a possibility that can be exploited nowadays. The other important approach for adaptivity is that you can use it to restore missing features. Now, what you see here is a very extreme example. Here we have a hand model, which is mapped to a simple cube. So all the major features of the hand, namely the fingers, are completely missing. And if you go for a uniform sampling, you have to be extremely dense in the sampling before you can even start to see some fingers arising. And probably the resolution that is needed for a uniform sampling to reproduce the whole fingers is such that the mesh doesn't fit your memory, because you have like extreme distortion in the mapping. So in this case, you can go adaptive. And if you just refine nearby the thin portion of the mapping where the fingers are collapsed, you can reproduce the model. Now, I don't think that this is a realistic use of this technology, but the point here that I'm trying to make is that we can try to be wiser than the classical polycube pipelines that essentially try to catch every single feature of the object into the polycube space. And this is very tricky, because you may have features at different scales. And so the idea here is that if you have like a polycube that catches only the major features of your object, you can still restore the secondary features with a little bit of extra refinement just where it's needed. And this seems to be like a good compromise between the complexity of your polycube and the complexity of your mesh. Also, because if you encode all the tiny features already in the polycube, like explicitly, if you apply a regular sampling of that polycube, you're going to have a much bigger mesh because now the size of the elements depends on the size of the smallest feature. So that could be a good argument to kind of balance adaptivity and polycube generation. Just final word to say that in terms of maturity of this technology, this is something that was started in the computer graphics community around 2010, 2011. We are now at the point where we can blindly compute polycubes for databases of shapes containing, I don't know, 100, 200, 300 shapes. So it starts to be reasonably robust. And that's why I believe that thinking about an industrial application of polycubization algorithms is something that can be pretty much realistic nowadays because of this increased robustness.
Okay, so the next method that we see now is field-based methods. So the idea is to find a suitable parameterization. So what is a parameterization? You can see here in the 2D example, suppose you have these arrows here, which is banded, and you want to embed, you want to parameterize this, and you want to map into a space where basically these cubes, these quads, in this case, are aligned with the UV direction, right? So once you have this mapping, you can cut the shape along parametric line in UV and get your quadrangulation. Similar idea works for volume mesh, right? You have this mapping, and obviously you can have also discontinuities, and this is especially true when you have singularities, like here in this case, you have this valency tree vertex. So this works more or less the same in volumetric mesh, but the trick is like you need to have a transition along singularities with some integer numbers of 90 degrees rotation and certain constraints. Don't want to go too much into detail, such that when this parameterization is assembled back to 3D or to the deformed space or to the space of the real mesh, so the tessellation will be smooth and continuous. So you have this smooth parametric line varying from one to the other. Okay, so how we can do like a suitable parameterization in general, right? So that's a very complex problem. You may think what you want to get a UV position, right, or of a mesh in 2D, or in 3D you have other kind of position, you have another coordinates, but you want at the same time to have good approximation of the mesh. You can have complex situation, right, where you have singularities, but you want to have regularity in general, and you want to have good element quality. Perhaps you want to control also the size of the elements. That is a very complex problem, right? So usually what you do, you're translating of this problem in finding a map, right? Optimizing a map. So how do you map this shape from 3D, right, or to one domain to another, where cutting through grid lines on 2D or a volume grid, you can get a parameterization, you can get a mesh with a nice element, which means the distortion induced by this mapping between these two spaces is small, right? And also you can change the metric, how distance are measured in this map, if you want to have different anisotropy and different sizing. So in the end, what this boils down is you have to solve a problem, so you have to minimize an energy that usually express the distortion of this mapping, and you have some constraints that involve some integer variables for like rotations or translations into this other space, because you can have, for example, some structures like the one we've seen before with an irregularity. So then you have to cut this irregularity in the UV space. That means that you have to add some constraints, which usually involve some integer variable in order to match one side of the cut with the other sides. When I say match, means that the parametric line that you cut in the UV map, they smoothly vary one to the other. So if you are interested into that, you can see the mixed integer quadrangulation paper that explains this concept map in much more in details, but we don't have too much time now here to go into detail. What I want to show you is like, if you try to solve this mixed integer problem in the general setup, it's very difficult because you don't have a guidance, you don't know how to align these elements, you don't know how to where to place singularities or where to place these discontinuities. There is too many variables, right? You can have discontinuities everywhere. So then the problem is relaxed in, okay, so let's first try to find a smooth frame field that guides data selection, right? And then try to align this parameterization and so these elements to this smooth frame field. So the problem is divided into a further step, makes the problem a bit more manageable. So then this is similar to problems of quad meshing in 2D surface embedded in 3D. Usually you start, this is the usual pipeline for quad meshing, field-based quad meshing. So you start with a mesh, then you have an orientation field that is used to guide, right, what is the main orientation of the triangle. And then you determine a sizing field. So it means like, what is the size of each element, how it's supposed to go in along this direction. And finally, you can get and solve a problem that involves some mixed integer problem with some constraints and find the quadrangulation that follows this orientation field. So the main problem now, it's like, right, I mean, we have a field right on the surface, but what is this field? So when we talk about surface, we talk about cross field, right? Here we can see like a vector field, and n equal to 1. What I mean with n is like a vector is invariant with respect to the rotation to 2 pi over n. So in this case, a vector of n1 is invariant to 360 rotation, right? And 2, you only express one direction, right? But it's also invariant to 180 degrees rotation, while for a cross field, the one that we use for quadrangulation is n equals to 4. There's also n equals to 6 that is used for triangulation. Similar to a frame field, you can imagine like having these small frames on the volume where actually you can like think of expressing this frame field in different ways because it's invariant of many different rotations. So this frame field is equal to this one, which is equal to that one, which is also equal to that one. That's the idea of a frame field, and you have basically 24 different rotation of that and equivalence rotation of that frame field. Okay, so now we have a frame field. We know that, and this is a crucial step, and most of the research now is focused on how to get a good frame field. And I'm going to explain you quickly why, right? So first of all, what we want for a frame field, right? We want to be aligned with boundaries, right? And we want to be as smooth as possible in the interior, right? Boundaries also curvatory directions on the surface, right? So there are several methods that can be used to derive volumetric fields, and they work pretty decently for Hex-meshing, but unfortunately, they are not stable enough, right? And they are not all the fields that you can derive with this method can be used to produce an Hex-meshing. And I'm going to tell you why, right? You start usually with a tetrahedral mesh, the pipeline of frame field Hex-meshing. Then you create a boundary aligned frame field. Then you map this tetrahedral mesh into an integer grid parameterization. So here you see a funny shape is distorted. Is how this tetrahedral map to the integer grid map that when you cut it through these integer lines, you get the hexahedral mesh, right? So there are several methods proposed in literature to go from the integer grid map to the hexahedral mesh, right? Or from frame field to get an integer grid parameterization. And these are more or less working very well. So, but the main problem is like this one. So it's always difficult to get a nice frame field such that you can solve an integer grid parameterization and get a final hexahedral mesh. And the problem is that the number of singularities that you can have for an HexMesh, right, the one that we have seen before, like the 11 case we have seen before, is less than the number of singularities that you can have in the frame field. So in the frame field, you can have like a huge variance of singularities. So the game is like, if you have some singularities that you cannot match, that you cannot mesh, right, you're going to end up with a very bad or degenerate elements, or you cannot map your 3D tetrahedral mesh into a integer grid map. So it's the final mesh that you get is degenerate. So we already discussed about this 11 configuration, and the game is that, okay, we want, right? We are pretty much sure that if we can map into this configuration, so we can solve the next problem. We can actually get a mapping from to an integer grid map that is actually Hex-meshable, right? And it doesn't have degenerate element. So Nizar and colleague started from this idea, and they said, like, well, you know what, we can actually create a field by creating a cage around the object, and then say, like, and this cage basically has the element as specified in the dual setup, sorry, in the primal setup. In this case, this as the topology of the field that I want to do, and I'm sure that because of this topology, right, the field would be Hex-meshable. So that requires sometimes can be quite tricky step of creating this cage around. But in the end, the meshes looks very, very nice, and the quality of these methods in field-based methods is very, very high. But there is still this problem of defining a suitable frame field, which is not yet resolved. There is some solutions. Another possibility is like work with a singularity graph. So you can sort of detect some configuration of the singularity graph that are not meshable, right, or that create some strange configuration, and then make some local modification, right, and also modify the field locally. So this is a bit better than before, but it doesn't guarantee that always with a set of local operation you can converge to a frame field that is like possible to mesh. So a more complex solution has been proposed by Liu and colleagues. So the idea is, like, obviously you still have a tetrahedral mesh, you have a smooth frame field, then you have a singularity graph, and then you create a corrected singularity graph, similar than before, but with a more complex operation. And then they actually created a nice way to automatically get a new field induced by this singularity graph, and obviously a set of boundary constraints like features. So, and at this point, right, you are guaranteed to get a nice hexahedral mesh. So the problem is, like, this part of correcting from a singularity graph general to a corrected singularity graph is still manual, so it requires like some effort from the user, and sometimes can be not very intuitive the way you can actually convert it to that. But one nice contribution in this paper is, like, this problem is already solved. So it's like the fact that given a singularity graph, how you get the constraint frame field that exactly match that singularity's values and exactly has the boundaries or sharp features is a solved problem. So then it remains to solve the first part, which is kind of challenging. But you can see that the when you can get a nice field, right, the quality of the mesh is very, very superior with respect to the other methods. Okay, so the next method that we are going to examine in this state-of-the-art report is called X-dominant, and it will group all the methods that actually create X-dominant meshes. As we show from the beginning, we discussed that the X-dominant meshes are meshes mostly composed by hexahedral element, but they can occasionally also include some non-hexahedral elements there and there. So, okay, so one first idea is that you may be familiar with like Voronoi tessellation with Voronoi partitioning with Lloyd relaxation. The idea is like you decompose a domain in a set of partition where each point, and you create a set of seeds, right? And each point belongs to the partition, or to the partition like encoded by the closest seams, right? Seed, sorry. And then you move this seed in the next iteration to the centroid of the partition itself. And that's called the Lloyd relaxation step. And if you do that, you can actually start from this random set of seeds, right? And then slowly convert to like a configuration like this, which is like hexahedral dominant, is called like this kind of organic pattern that we always see when people talks about Voronoi mesh tessellation. But the idea by Levy and colleague was, look, instead of using like a distance metric, right, which is a circle like L2, why don't we use L infinite, right, or L like with a high exponent on this equation that you see below. So if you do that, right, the distance matrix, like instead of being a circle from that point, you can see the isoline, they variates and they tend to be like a square, right? So this idea changed basically the way you measure distance within the domain. So then if you do so, you start from this, right, and this distance, and you can end up with that, right? And obviously, you may guess that this is a very powerful tool that you can use in 2D and almost quickly and immediately translate to 3D without any problem, right? Because you can immediately create hexahedral cells. So, and obviously, when you have this complex here, you can take the dual of that and you can have your hexahedral dominant mesh, right? Obviously, it's dominant because that doesn't guarantee that you have all your cell hexahedral. You still insert some general polygonal mesh. So here is an example of what happens if you change your distance matrix video made by Bruno Levy. If you actually start from a quad elements and you slightly perturb, it converges to the usual Voronoi configuration if you use the usual norm. But if you change the norm, so then the square configuration is pretty stable, right? And you can actually insert more cell, and this cell will like dispose in the space as a regular grid. And you can do this on a surface, right? Or you can do this on the volume as well. So this is an example how you can use that in the volume, right? You can distribute the seeds into the volume, right? And then create this set of partitioning and then subdivide this partitioning. You can have as much high resolution mesh as possible. So there is another possible polyhedral agglomeration strategy, which is very interesting. And this is in between like a field-based method and an agglomeration method, because it still uses a field, right? But it actually creates hexahedral dominant meshes, and it tends to agglomerate like tetrahedral inside the volume. So the idea is like you create three different scalar fields, and these scalar fields are U, V, and W, right? Imagine like if you have this solid here, you create this three scalar field, and then you can cut in different direction on isolines of this parametric field, and then you can get your final hexahedral mesh, right? So the main problem here is how you can find this field to be smooth, right? And obviously also driven and like also oriented along a frame field, which is also follow, as we've seen before, defined to follow sharp features and curvature. That's the main problem. So you actually, when you have it, right, you can apply grid texture and get your final mesh. So this is the extension of periodic global parameterization, which is a very nice method to create quad meshes, right? In general, you can use this periodic function over the surface, a sinusoid or a function over an angle that goes over the surface, and in certain direction, you have to understand how this goes, right? So that you have like this set of different isolines at different frequency over the domain in one direction, and then you can do for the other directions in a way that you can get the quadrangulation. You only need 2 for volumetric, you need 3. So basically, the idea here is to map the surface into a circle parameterized by that. Okay. So this works also for complex models. So as you can see here, there is this very complex model where you have tons of elements, and it works with create high resolution meshes. And you can see here it creates several non-hexa meshes, usually maybe in correspondence of singularities, but not entirely true. It can also create like singularities all around. So another method is for polyodic agglomeration that create X-dominant mesh, has been proposed by Xifeng and colleagues. So you can start with a input tetrahedral meshes, right? So this method also defines a cool way to find an orientation field, but this is not part of this survey. There is also a lot of literature on orientation field, but this orientation field find a position field. So it means like you can actually want to you actually define a target position for each vertex of a tetrahedral mesh, and then you can extract the mesh by a set of local operation that modify the connectivity of these meshes. So to be actually more clear, the idea is like you deform the tetrahedral meshes such that each vertex, it will be allocated to a certain target position, right? In the end, you get this extremely deformed, tessellated tetrahedral mesh that you can actually do a set of local operation so that you can extract your HexMesh by collapsing the tests which are not nice. And then you can have your final hexahedral meshes. Obviously, you can see here there is a triangular face, and that's exactly what happened with X-dominant meshes. So they have elements which are not hexahedral. And not always you can actually solve them by subdividing. But this method demonstrates extreme robustness, except for the fact that it actually uses quite a lot of singularities, non-hexahedral meshes, non-hexahedral cell. It's very, very robust, and the quality of the mesh is quite good. So recently there was this other paper by Buchenberg and colleague that presented recently at Eurographics. So the first idea is like, okay, so we have Voronoi partitioning with Lloyd relaxation with L2 norm, right? We have seen also the L infinite norm, where basically tend to align these cubes to a certain and create a quadrilateral pattern. But you can actually also have L infinite norm plus orientation, right? So then you can actually orient your cubes in different direction in your domain. So you can follow a field, right? Or you can follow some external features, which make this infinite norm much more interesting to use in the context of Hex-meshing. So the problem is, like, when you have this set of cubes, you will see that they will never really match, right? It like looks like a bit, if you have seen from the previous slide, it looks like a bit juggled around. So the idea here is like make each cube sort of independent and then try to stitch them together on the edges by considering the local configuration. So when you have these local patterns where you can always find a set of neighbors for each cell, so this immediately boils down to some nice X and regular hexahedral tessellation like this one. But when you have some strange situation where you have a reduction of the density, right, from one side to the other, then you have necessarily, in order to have a conformal mesh, right, because the one you see here is not conformal, you have necessarily to add a non-hexahedral meshes and to change the resolution from one to another. So there are also other cases, particular case to manage features, right, and all the other kind of configuration close when some element is close to the external surface. So in the end, one nice thing about this method, it can always guarantee to get also, yes, non-hexahedral elements, but these non-hexahedral elements are within a certain class of elements. So it can be a prism or tetrahedral or 6 prisms. So you know which kind of elements you're going to end up with. So here we can see some results. Results are pretty nice, but still it inserts quite a few non-hexahedral elements there and there. So it can be used in some context, but obviously it requires an FEM, which is more complex than a usual FEM that only use hexahedral elements. Okay, so here we discuss a bit advantage and drawbacks of each class of methods that we have seen right now. So first, we start with the advancing front methods. So obviously, they are designed to preserve features, right? Because they start from the border to the interior, but there is no guarantee that, and also if the border is decently aligned with the curvature, it tends to guarantee that the curvature can be preserved in the interior, but it's not robust, right? Because it needs a lot of tricks to manage when different fronts together they meet each other's, right? Obviously, it doesn't allow us to have a core structure. When I mean core structure, I mean block decomposition, right? And you cannot guarantee it to be all X because you can have some strange situation where I mean, it's like the fronts can create some strange situation where you cannot guarantee that mesh is all hex. So dual approach we have seen right now, it preserves features very well because it's start sometimes cutting the mesh from the features like loopy cuts or like the approach from Takayama and colleagues, the manual one. And also they are nice because they create a core structure, right? So they are designed to create really nice core structure that subdivide the volume into parts. But sometimes they can create all Hex-Mesh, and even the robustness is not guaranteed, right? Especially loopy cuts. Sometimes it can introduce non-hexahedral cell, right? So robustness is not has been demonstrated in very exhaustively in this kind of methods, right? The quality of the hexahedral is good, and also the curvature alignment is good if you actually try to align the sheets, right, that you cut in the dual domain to curvature directions. So block decompositions have good X quality because usually you need to have this predefined minor tessellation for a block, right? They can align to the curvature decently, Obviously, they are limited sometimes to the kind of mesh they can do. For example, for this block decomposition of skeletal meshes, you cannot use for different kind of meshes rather than these organic particular shapes. They can preserve the features if you want for some block decomposition that are exactly start from feature lines. And yeah, they are robust, right? And they can create all X in most of the case. But I mean, I wouldn't put too much because they are not general. So they can be used only in some configuration and particular 3D data. They are not general enough to model any kind of input data. So the grid meshing method, they excel for robustness, right? And they guarantee to use X meshes. So basically, as Marco explained it before, you overlay the mesh with the grid and you start cutting. Nothing bad can happen if you create your operator in a robust manner. They can preserve some feature, but not always, because feature transfer, it might be a problem for that, how you can transfer a set of continuous feature to some edges of your grid. And obviously there is no core structure here, so you tessellate for each cell independently. That cannot guarantee curvature alignment, and the quality is really bad because usually you end up with a lot of singularity. Polycube has nice X quality, nice curvature alignment. They produce all X, but they're not, and also they have core structure because you can map these big cubes into chunks of smaller cubes. But unfortunately, right, they are not entirely robust and they cannot preserve any kind of feature configurations because they have to map necessarily to a polycube, and not all the configuration of features of a mesh necessarily map to the edges of a polycube, right? Even curvature alignment is somehow good, but limited by the fact that you have to map to a certain configuration that it conforms to the space of possible polycubes embedded in 3D. Field methods are really promising, right? Because they have nice X quality, curvature alignment for free, feature preservation, core structure, yes and no, right? It depends, but if you can make low tessellation, it's possible. But they are far from being robust, right? I mean, it's like if you apply with a lot of meshes, right, only a few ones will automatically, right, can be obtained. Obviously, if you design your field manually, you can do that, but that's a kind of hard task. And the fact that it's all X is limited by the fact that for certain field configuration, you cannot guarantee that it's all X meshes that you get it. Okay, so the next argument that we are trying to discuss today is the visualization of HexMesh, which seems to be quite simple, but indeed is not, because it's different from a triangle mesh or a surface mesh. Visualizing a quad mesh can be challenging because you actually want to inspect what's happening inside, and so you need some tool to explore the HexMesh, assess its quality, and different characteristics of that. So there may be several motivations. The first one is like you want to visualize the result of some FEM experiments, or you want to inspect and check the quality of your meshing algorithm to see if it actually creates some degenerate element or not a nice structure inside. You can also plot histograms to show or statistics about the quality of the elements, or you can actually also just visualize the data for a paper or for some industrial context. So one of the most common tools for visualization, which is nowadays available to the public, is called XLab. And that's a system that me and Marco here collaborated to deliver. And it's basically a web-based system that runs on a browser. You can check, and it actually have most of the meshes that has been processed right now from most of the SIGGRAPH or computer graphics paper on HexMeshes. So you can go there, and it also acts as a repository. There is a lot of mesh from the last 10 years of papers on hexahedral meshing. And it uses a sort of a trick for rendering it to make the overall experience more understandable in terms of understand what is the structure of an HexMesh. The first one is to use the ambient occlusion. So here you can see like a trick that people use also in molecular visualization. So when you have a set of different entities together and it's difficult to understand what is the overall shape, what you do, you apply ambient occlusion to the mesh, and that gives you like an overall shading that helps you to understand what is the overall shape of the object. So we actually applied a similar concept here to HexLab to visualize, for example, this difference from without ambient occlusion or with ambient occlusion. Obviously, you can see that with ambient occlusion, you can better perceive what is the shape of the hexahedral tessellation. So another trick that we applied is like we took inspiration from how the bricks are organized together, and we try to leave a bit of space between one cell and the other, so it gives you more the impression of the volumetric field, and also you can see how the internal configuration evolved for a bit. Obviously, we also have in HexLab also have some tools to explore the interior of object. For example, the classical slicing plane. You can slice through an object and visualize the tessellation, or you can do peeling, right? You can actually remove entire layers of hexahedrons from outside to inside to visualize the main structures of the object. So there is also a tool to visualize connectivity. So you can, for example, visualize the singularities in with different colors depending on the valence of the edge, right? And at the same time, you can also visualize together, or you can show or decide to occlude the one that are not visible by the part of the mesh that is not visible, or you can decide to visualize all of them if you want to have an overall structure of the mesh. So there are different possibilities. So another important characteristic of HexLab is that it implements all the different X quality, like measures commonly shown in literature. And there is also a possibility of visualizing statistics and distribution of different elements among the different level of quality, and also color the mesh or isolate certain elements on the mesh that has low quality. So it's possible to inspect if a particular element, for example, has caused some problems to an FEM simulation. And another characteristic of HexLab is you can actually take your model, right, bring it to MeshLab, right, and use the same kind of visualization that you use to visualize a similar model or a similar hex mesh. Just with copy paste between windows, you can copy paste the different same visualization strategy with the same characteristic from the same camera. So you can actually get a model right from all the literature, and you want to compare with your model that you created for your new algorithm, right? You load the first one, you slice, you color as you want, then you open another window with your model, copy paste, and you have the same visualization. There is even more complex visualizer online, which this paper by So and colleague, which actually it's more focused on the structure. So these guys, what they're doing, they're trying to create a matrix that shows how different blocks or different sheets of elements or chords, like streams of Q of X in the primary, in this case, not exactly like in the dual, they interact each other, and they find to optimize and they try to find an optimized view of all them together. So they use a kind of a matrix that shows how the different parts interact with each other. And this is an even more complex paper that used shaders and advanced rendering technique with transparency to also visualize internal elements. So it used a combination of blurring and transparency, and perhaps visualize more in details when the elements are degenerate or doesn't have a good aspect ratio. So this is a nice another tool which also use advanced rendering technique and model shaders.
Okay, so this is the final session of this presentation, and we're going to discuss open problems in the field of hexahedral meshing, and also some suggestion for future works, so things to look forward to ameliorate in some regard. Well, I'm going to start with mentioning some theoretically challenging problems that are still open, especially in the field of frame field approaches and polycube approaches. And then I'm going to go towards more practical problems for which maybe we do already have algorithms that kind of do the right thing, but we will just try to make them better because it's beneficial for this field. So let's start with the first problem for frame field approaches, which is the X-ability of a frame field. So as already mentioned Nico during his presentation, the space of frame fields that admit an hexahedralization is actually a smaller space with respect to the space of frame fields. That said in other words, it means that if I ask an algorithm to compute a frame field, I actually don't know whether that frame field admits an hexahedralization or not, and the conditions under which this conversion from phase field to hexahedral mesh is possible are not yet clear, or at least not completely. So that's a huge issue. It's not only that we don't have methods to do that, we still don't know exactly what do we want to do. Now, a typical failure case that is an exemplification of this issue is what is called the 3-5 valence problem. So let's say that I have a shape like this, in which essentially here I have a cube, and I'm just cutting a little wedge with this rounded shape here. And in terms of mesh generation, the best way probably to mesh this thing is to have a valence 3 vertex here in red, just to accommodate this kind of triangular shape. And here I'm going to have kind of a pentagonal face shape, and so I'm going to put a valence 5 here. Now, if you go with the surface meshing, surface quadrangulation, this is pretty much the best thing you can do. And volumetrically, you can imagine that the best thing to do is to just propagate inside the volume these singularities, such that you have like a line that starts from here and goes to the very bottom, and a line that starts from here and goes to the very bottom. So that's what we would like to have, and we will know how to hexahedralize. The problem is that when you compute a frame field, there is a weird thing happening, because now you get a singularity that starts from the top of your shape and starts as a valence 5. Rather than going just down to the very bottom, it takes a turn here and goes up again to show up as a valence 3 singularity. So along this singularity, you start with the valence and you end up with another valence. So this is perfectly reasonable in the space of frame fields. But of course, if you try to give an interpretation of this behavior in terms of an hexahedral mesh, this is just impossible. So what you are trying to do here is essentially to have a chain of edges in your hexahedral mesh, in which in the beginning you have 5 hexahedral elements attached to that edge, and then you take the subsequent edge along this chain, and you have 3 elements. That's just impossible. You cannot find a conforming mesh that has this behavior. And so this is going to be a failure for the conversion from the frame field to an hexahedral mesh. Another typical failure is what is called the presence of a limit cycle. So whenever you have kind of a rounded shape like this with a stair, what happens is that if you propagate or if you trace an integralized line that aligns to a field that is computed here, you get a limit cycle. So something that is just running around itself and never stops. And of course, this is not going to define any good mesh. So these are 2 well-known defects that arise when you compute a frame field, and you would like to be able to compute a frame field, at least for HexMesh generation, that is guaranteed to be free from these defects. There are also probably other issues. It really depends on the shape from which you start. And so already from a theoretical point of view, it's really unclear how to develop and how to have like a more stringent definition of hexable frame field. Another important theoretical limitation of current approaches, in this case, we're talking about polycube approaches, is a topological characterization of polycubes. So as I said in the presentation regarding polycubes, what you would like to do when you define the structure of your polycube is to be able to say, okay, this graph, so the set of corners and edges that are defined in the separation between the charts in my polycube segmentation, define or do not define a valid polycube. And this is a graph characterization problem, which is quite abstract and has been looked for already by researchers in the field of graph research. And the results that we are aware of start from a very famous theorem that is called the Steinitz theorem, in which essentially Steinitz said that the graph is the skeleton of a convex polyhedron. So it defines the vertices and edges of a convex polyhedron if and only if it is tree-connected and is planar. So it can be embedded on the plane, and every single vertex contains 3 nodes. And in order to separate two components from this graph, you need to detach at least 3 arcs from vertices. There was an extension of this Steinitz theorem. There was kind of a specialization for orthogonal polyhedra, and it was done by Epstein and Mumford in 2009. And these more recent results says that the graph is the skeleton of a simple orthogonal polyhedron if and only if the graph is bipartite, planar, irregular, and the removal of 2 vertices creates 2 connected components at most. So this is a much more complex definition to address algorithmically, but at least is a characterization of some part of the polycube structures that we are interested in for hexahedral mesh generation. The problem with this definition, besides of this complexity, is that it doesn't cover the whole space of shapes that you're interested in, because it covers, for example, these 3 classes of orthogonal polyhedra, so corner, XYZ polyhedra, and simple orthogonal polyhedra. What doesn't cover is shapes like this, which are non-triregular because this point here has 4 incoming edges. So the valence of this vertex is 4. So this is beyond the theory of Epstein and Mumford. And also objects which have a non-trivial topology, like kind of this ring here, are not contemplated into the topological analysis of Epstein and Mumford. But these are still polycubes that we would really like to have and to be able to define, because they are important for applications, right? Having genus, having higher valence vertices is very important for CAD objects, for example. Most recently, in 2019, there was this paper, Polycube Shape Space, in which essentially this classification was extended to objects with non-trivial topology. But still, polycubes in this category, so having, for example, vertices with valence 6 or with valence 4, there is no clear topological classification, so it's always difficult to state whether we have a valid polycube or not. And this is an issue because, as I said, especially in CAD modeling, having sharp features in this configuration is actually quite common. And if you're not able to preserve these features, you are likely going to create a mess here with the polycube, and you are going to miss all these features, which is actually a very bad thing. So this is probably an open challenge more for people working in theoretical graphs than people working in computer graphics, but still, it's something that is very interesting for practitioners like us that operate with polycubes for these applicative reasons. Another important problem that has to do with all the indirect algorithms for HexMesh generation is issues with the generation of a proper volume mapping. So indirect methods are methods that that operate, for example, on a tetrahedral mesh and use a tetrahedral mesh as a domain to eventually define an hexahedralization. And all these methods, the most trivial examples are polycubes and frame field methods, use a volumetric mapping to transfer the connectivity from one space to the other. So they necessitate a mapping that is injective, because otherwise, when you bring elements from one space to the other, elements that are not touching in one space may overlap in the other, or maybe elements that may become degenerate in one space, and so they will have zero volume, they will become non-physical. So for all these reasons, we need a mapping that provides some guarantees. The problem is that the volume mapping problem is a very challenging problem, which is relevant in computer graphics for countless reasons, and this is just one specific application. And to my knowledge, the only algorithm that is able to provide guarantees on the fact that the mapping being computed can be is injective, is guaranteed injective, is the algorithm called simplicial foliations that was published by Marcel Camper and colleagues back in 2015. But still, this is not enough for what we need, because simplicial foliations define mappings to very simple objects like a sphere or a cube like this. So this is already not flexible enough if I want to compute a mapping between, for example, a bunny and a polycubization of the bunny. And there is also another issue. And the other issue is that this mapping is non-linear in its very nature. And if I want to kind of linearize it, which means if I want to represent it into the connectivity of a tetrahedral mesh, I have to apply a massive amount of additional refinement. For example, if I have a shape like this with 1.7K tetrahedra, and I want to encode a mapping to a simple cube into this connectivity, I'm kind of growing 2 orders of magnitude, and now I have 1.1 million elements in my mesh. So that's a lot, and it's impractical, because you can imagine that we want to work with the meshes which are much finer than this, and so we're going to end up with something that is completely unbearable for many algorithms. The alternative for this specific problem is to apply what is called mesh untangling algorithms. So the difference here is that mesh untangling algorithms take a mesh, for example, a mesh that is mapped from one space to the other, and if the mapping was imperfect, we have collapsed elements, we have flipped elements, and these methods are able to recover a valid shape for all the elements in the mesh. And in recent years, these methods, especially Garance et al. 2021 and Du et al. 2020, have now become extremely robust in doing so. Here you can see, for example, that starting from a shape that is essentially 2 nested cubes, here they are computing mapping to shapes where the inner cube is rotated by 45 degrees, 90 degrees, up to 180 degrees. So this is a huge deformation, and still this mesh does not contain any inverted or degenerate elements. So the power of these algorithms seems to be extremely promising, but still we're talking about heuristics, and so there are no guarantees that this method can do what we need. I think that as of today, this is probably the best attempt that we can have in our polycube pipelines or frame field pipelines, but still no guarantees of correctness. There is also another alternative, and in this case, essentially, the assumption is that, okay, I'm not going to trust my simplicial mapping. I'm just going to compute a grid, for example, in polycube space or in my integer grid map, and then I'm taking the elements from this mapping and just bringing them back to my shape. And these elements are going to be, hexahedra, are going to be extremely bad because they will be badly shaped, distorted, and then inverted, and so on and so forth. And so now I can try to do the same untangling approach, but already in the HexMesh connectivity. So this is something that we tried, for example, back in 2015. It worked kind of not bad. It was decently powerful. It was able to recover from many challenging configurations, but still, as for untangling algorithm for tetrahedral meshes, also in this case, we are in the realm of heuristic approaches, and so we have no guarantees of having the correct result. The problem is that when you want an injective, at least a local injective mapping, what you are trying to constrain is the determinant of the Jacobian, which is a 3x3 matrix. So we're trying to deal with kind of cubic constraints, which is, of course, extremely nonlinear and non-convex problem. And so you need to kind of relax your problem in order to be able to compute something. And in the moment in which you relax, then you lose all your guarantees of correctness. Okay, other problem, always connected to indirect approaches such as polycubes and grids. Here the problem is that I want to transfer the features from my input shape to my output hexahedral mesh. And since these approaches are indirect, so they are not guaranteed to conform to an input quadrangulation or something like that, we have to apply what is called a feature transfer algorithm. And in particular, what we do is to find all the features in the input shape, and we have to assign these features to chains of edges in my hexahedral mesh. In this case, I'm taking as example a mesh that was computed with an gridbased approach. And you can see that now these features belong to kind of these staircased lines, which are just chains of edges in this grid. What is the problem? The problem is that the way we do this is heuristic, and essentially the current approach is to go sequentially. You take, for example, you start from the longest feature possible in your mesh, you try to map it, and then you put the second one, the third one, and anytime you put another one, you may have conflicts with the previously inserted ones because the connectivity of the mesh in which you are reproducing the features is different with respect to the connectivity of your original mesh. And anytime you have a conflict, it can be like a conflict that you can resolve with a detour, or it can be a conflict where essentially there is no way to complete your feature. And in that case, you need to skip that feature. In both cases, you're going probably to produce horrific results. And this was shown, for example, in this paper, which does something similar. It's a layout embedding problem in which, let's say you have a bag of features that you want to map on your surface. And if you are not smart enough in picking the right order in which you want to create your features, you can create just horrible reproductions of this structure. So I think that going like in this direction, which is using a branch and bound approach, is actually very promising. This approach in particular was never tried in pipelines for feature transfer associated to hexahedral meshing in general, but I think it would be a nice starting point, and maybe there is something more to do in this direction. So I'm really interested in actually exploring this direction of research. Another important thing that I would like to discuss is, so since we know that, by now we know that computing an hexahedral mesh, it's a very complicated matter, and actually the algorithms that we have, they pretty much all fall short in something. There is a parallel line of work, which is about, I'm gonna manually create my hexahedral mesh through some user interface. And this is pretty much the standard in the industry because of a lack of a robust and reliable and high quality tool. How do these methods work? Here I have a few snapshots from a video that was, it's essentially a webinar for the Qubit software. Qubit is probably the most prominent semi-automatic tool for computing hexahedral meshes. And I want just to show how these methods work and what are the difficulties with these approaches, because I think that additional research in this field might be extremely important. Let's say that in this case, we want to compute an hexahedral mesh of this object. It's a very simple object, right? We have one cylinder here and two cylinders that are attached laterally and are like smaller in size. If you try your luck and you say, okay, go and HexMesh it, what happens is that this software, Qubit, is going to show you the parts where it succeeds, and it's essentially where you see some elements. And where you don't see anything, it means that this part is actually not meshable according to the software. Okay, so first attempt failed. Fair enough. And so typically what you will do is to produce like a domain decomposition in order to split your element, which is considered to be too complex, into simpler pieces. And the idea is that you keep iterating on this approach until every single element in your decomposition is simple enough to be meshed separately. And so the union of all the meshing of all elements is going to give you the final mesh. And so you split here, you split here, you split here, which is a pretty standard splitting. We're just splitting like with axis aligned planes. And now we can imagine every single element is going to be meshed separately. We try, well, same result. We can compute a mesh for all these subdomains here, but these subdomains here are still failure cases. We don't see any mesh. Okay, so now the process, as I told you right now, would be to continue splitting. And here comes a surprise, because actually the the author of the webinar takes a single domain, just changes a command, and it's able to mesh this. And what he said, it's actually, it was pretty surprising to me, because this is a quote from the actual video. He said, "This is a case where Qubit wasn't able to determine automatically it could build a polyhedral mesh, but I kind of knew that it could." So what does it mean? It means that to be a proficient user in this and to be successful in producing a good hexahedral mesh with these kind of tools, not only you need to kind of master the tool, but you need to be so expert and so inside the technicalities of the field that you need to know better than the software itself what the software can do. So Qubit wasn't able to know that it could mesh that particular object, but it actually could, and by forcing the operation, it was able to show the software that the software was able to do that. Now, this is not very useful, because the learning curve of a software that operates in this fashion is actually horrible. So we need to be able to develop and to deliver tools that are better than these. And I perfectly understand why this is happening. The reason why this is happening is that these methods internally use tools which are heuristic to compute the hexagonalization of every single element. But the problem is that if the tool is heuristic, I can never know and I can never predict whether I'm going to be successful or not until I try. But I cannot try every possible algorithm that I have implemented just to let you know that I can do that or not. It's going to become like a disaster, because it doesn't work essentially. And so we need to be smarter at this, to provide maybe different kind of user interfaces, maybe different combinations of algorithms. But this thing was actually super surprising to me. And so eventually the mesh was computed. There was still a little bit of struggling to obtain full mesh conformity, but the crucial point was that the software didn't know that it could, but the author knew, and so he made the software do what he knew it could do. And I suggest all of you, if you are interested in the field and if you're interested in developing user interfaces for hexahedral mesh generation, to take a look at the video. It's pretty long, maybe it's about an hour, and it shows a few examples. This is one of the simplest ones, but it's very instructive on what is the state of the art in the field, and maybe new ideas will come out just to what not to do and what to do, like they're doing right now. Okay, a few words on the robustness of current approaches. So as we said during the discussion of the various methods, I think that by now it's clear that grid-based approaches and X-dominant methods that operate by agglomerating tetrahedra are kind of unconditionally robust. So they can mesh pretty much anything. And here you can see two extremely complex shapes. Like this is a whole block of an engine, and this is like a complex mechanical part that was meshed with an object-based approach. No other method is actually not even close to these methods in terms of robustness. So we need to do much more in order to increase the robustness. And this will go through, more abilities in the feature transfer, more ability in the volumetric mapping, solving theoretical challenges for polycubes and frame fields, and so on and so forth. Just one word on the utility and the hope, at least for me, that in the future there will be more and more of these initiatives for data sets and benchmarks. XLab is something that we created a few years ago. It's now very popular, not only for visualization, but also as a database of state-of-the-art results. So we're super happy to see that anybody is publishing new algorithms for hexahedral mesh generation is actually loading their models in the database. And so the database is aligned with the state-of-the-art. And if you haven't tried it yet, I suggest you to connect to www.xlab.net. And just to make an example, you get visualization of hexahedral meshes like this, and you get a database of pretty much all the interesting papers in the field in the last 10 years or so. And here is another initiative by David Bombs and other colleagues. And it's a different thing because this is a database of hexahedral meshes. And so it contains results of algorithms. This is a database of inputs for algorithms. And here the challenge is I'm going to give you shapes of varying complexity from simple to less simple to extremely challenging. let me see what you can do. And this is amazing because it's going to challenge people. People are going to try to make better and better and better. And so eventually algorithms, crossing fingers, will be able to actually HexMesh it all. So the whole database. And as I said, I'm looking forward to see more and more initiatives of this kind. Just a final word regarding novel applications. In essentially the entirety of the course, we talked about hexagonalization algorithms in terms of inputs for PDE solvers, because this is like the killer application of hexagonalization algorithms. But in reality, we have seen that, especially very recently, these are like 2019, 2021, 2022, advances in something that is related to hexagonalization, for example, frame fields, have triggered new solutions that for things that are not related with PDEs at all, like fabrication of microstructures, topological optimization, and so on and so forth. And so we're super happy to see that, for example, the advancements in the frame fields are inspiring other research in other fields. And this is very interesting because you know, if we all develop the theory and everybody uses the same theory for different things, and so we will proceed faster. So we're looking forward for other people figuring out new connections that we don't foresee yet. And with this, I thank you all for the attention. So I thank you by myself and also on behalf of Nico Pietroni, the other author of the course. And nothing. Thank you. I hope you enjoyed the presentation. Bye-bye.